Hello viewers, welcome back to the course on scientific computing using MATLAB. So, today we are going to start with the lecture 18 and we are going to start with the next unit. So, this is about linear equations and eigenvalue problems. So, in this case we are going to deal with the first with the linear equation. So, suppose we have a system like Ax is equal to B, because you must have seen this type of system anywhere, most of the places, because whenever you are dealing with the, like I have this equation 3x plus 2y plus z is equal to 2x plus y minus z is equal to 3, or maybe I can take 2.5x plus 3.1y plus 9.8z is equal to 4, like this one. So, I do not know that whether the solution exists or not, but suppose I take the like this one. So, this type of equation you can solve, because I can write this system in the form of Ax is equal to B. So, in this case my A is 3 by 3 matrix and x will be the, so I can write this system as 3, 2, 1, 1, 1, minus 1, 2.5, 3.1, 9.8. So, this is my equation corresponding matrix, and from here I can write my x, y, z. So, this is the values we are going to find, and on the right hand side I have a vector. So, that is 2, 3 and 4. So, this is a system, linear system of equation which has, in this case, deal with the 3 by 3 matrix, and that is 3 cross 1 and this is 3 cross 1. So, this is a column vector, this is a column vector, and that is a matrix. So, now we know that if I have to solve this system, and then if the determinant of A is non-zero, so it is a non-singular matrix, then we can solve this system. So, this system I can solve as, so this system is A, x is equal to B. So, now if the A is non-singular matrix, I can pre-multiply this with the A inverse, and I know that A inverse A is equal to I, that the identity matrix. So, from here I can write my x is equal to A inverse B. So, this one we can do, we can find the inverse, and the inverse we can find with the help of adjoint. So, we also know that how to find the A inverse. So, A inverse basically I will find the adjoint of A divided by the determinant. So, this is the way we generally solve the 3 by 3 system, and what we have done in the school level. Now, the things have changed, because now what will happen, we may have a system A that is n cross n. So, it is a, suppose it can be a very large system, and this is my vector n cross 1 and this is equal to B n cross 1. So, that is my system, and n can be very large. So, in this case, now it is very difficult to find the inverse of the matrix, or even if it is very difficult to find whether the matrix is a singular or non-singular. Suppose somehow we find that it is a non-singular, then it is also very difficult to find the inverse for a very large system, even with the help of the computer. So, in this case we are unable to solve the system, then we have to use different methods to find out the solution of this system. Now, suppose I take a matrix A as D, the diagonal matrix. So, my matrix A is a diagonal matrix. So, let us write this system. So, in this case my the matrix will be A11 and x1, this is equal to B1. Next will be A22 x2, that is equal to B2, and the same way it will be ANN xn, and that is equal to Bn. Because my matrix A is here is a diagonal matrix, that is A11, A22, A11, A22, A33 and ANN, and all other values are 0. So, my matrix is a diagonal matrix, and based on the diagonal I will get this system of equation. So, from here you can see that I can solve this equation exactly. My x1 will be B1 by A11, provided my A11 is not equal to 0. So, the same way I can find all the value of xi with Bi is equal to Aii, where I am considering my Aii is not equal to 0. So, that is the solution we are able to find. Now, in this case it does not matter, because my matrix is a diagonal matrix. So, it can be a very large system, but for the very large system, if the matrix is a diagonal matrix, we can find the exact solution with a very small time with the help of this one. So, this expression gives you the exact value of the solution. So, we are able to do this one. So, I can write this as a case 1, because my matrix is a diagonal matrix, a very simple matrix. So, let us take the another example, case 2. So, in the case 2, suppose I have my matrix A, and that is equal to the lower triangular matrix. So, L is equal to lower triangular matrix. So, lower triangular matrix means I have A11, A21, A22, A31, A32, A33, and if I extend this one, so it will be last AN1, AN2 up to ANN, and all other terms will be 0. So, this matrix is basically, if you see, then this is the values of the elements in the matrix, and all the elements above the main diagonal are 0. So, this is a lower triangular matrix. Similarly, we can define the upper triangular. Upper triangular matrix. So, that would be U. So, in that case we have, this is the main diagonal, and all the non-zero elements are lying here, and below the main diagonal all the elements are 0. So, this is called the upper triangular matrix. So, let us say that A is a lower triangular matrix. So, if it is a lower triangular matrix, then my equation will become like this one, A11 x1 is equal to B1, or I can write this as equal to B1. Next will be A21 x1 plus A22 x2, and that will be equal to B2. Next will be A31 x1 plus A32 x2 plus A33 x3 is equal to B3. So, the same way we can write the last nth equation. So, this will be N2 x2, and in the last ANN xn, and that will be Bn. So, this way we can write this system. Now, if you see clearly from here, then from this equation I can find my value of x1. So, x1 is B1 A11, provided A11 is not equal to 0. So, I am able to find the value of x1. Now, from here I know the value of x1. So, I can find the value of x2 here. So, that will be B2 minus A21 x1 divided by a22, provided a22 is not equal to 0. So, once I am able to find the x1 from this step, I will substitute the value of x1 here, and from here I am able to find the value of x2. Now, from here you can see my x2, my x3 from here will be what? x3 will be equal to b3 minus a31 x1 plus a32 x2 and then divided by a33, provided a3 is not equal to 0. So, from here I can write the last one is xn can be written as bn minus summation. So, this summation is there. So, I can write from here a n1 x1. So, I can write from here j, and j I can write from 1 to n minus 1. Okay. So, this one divided by a n n, provided a n n is not equal to 0. So, from here I can find the value of my x n. Exactly. So, from here I can see that I am finding my solution in this way, in this direction. So, this is called the forward substitution. Means I am first finding the value of x1, based on this value of x1 I am finding the value of x2 and so on. So, we are starting with the x1. So, that is called the forward substitution, and the system is able to solve using the forward substitution. So, in this case also you can see that we are able to find the value of the solution exactly even for the large number of systems. So, the same case I can do the third case when my A is equal to u, that is the upper triangular. So, in the upper triangular matrix, what will get? I will get my system of equation as a11 x1 plus a12 x2, and in the last a1 xn is equal to b1. Next equation will be a22 x2 up to a2n xn is equal to b2. And the next will be a 33 x3 a 3n xn is equal to b3, and if we go the same way, the last one will be a nn xn is equal to bn. So, in this case also I am able to find the root, the solution of this system starting with the last equation. So, that is a xn. So, this will be bn by ann. Now, if I am able to find the value of xn, the next to this one will be a n minus 1 x n minus 1 plus a n n x n. So, before that my equation will be x n minus 1 a n minus 1 n minus 1 plus a n minus 1 n x n is equal to b n minus 1. So, what I will do? I will substitute the value of x n here, and from here I can find the value of x n minus 1. So, x n minus 1 will be b n minus 1 minus and then divided by a n minus 1 n minus 1, provided a n minus 1 n minus 1 is not equal to 0. So, in this way we are able to find all the values of the variables x1, x2, x3, and the direction of the variable will be from down to upward. So, this process is called back substitution. So, now we have seen that if my matrix A is of the type D, L, U, then we are able to solve the system very easily, and then we are able to find the solution exactly. So, our main purpose is now to transform the matrix. So, this is my matrix, that is n cross n matrix, and what I will do, I will from this matrix, I will convert this matrix, transform this matrix either in diagonal form in the lower triangular or in the upper triangular, and then we are from here we will be able to solve the system very easily. So, that is our purpose now, to solve the system. So, if I am able to do this one, then we will be able to solve the system exactly. So, this is our purpose now. So, now before we are starting with the process, so let us define some, discuss some properties of the lower triangular, diagonal or upper triangular matrix. So, in the lower triangular matrix, now let us start with the L is equal to lower triangular matrix. So, let my L is L11 0 0 0, L21 L22, this is Ln1 Ln2 and so on Lnn. So, this is all 0. So, this is my lower triangular matrix. So, in the lower triangular matrix, the determinant of lower triangular matrix is just the product of the diagonal elements. Okay. Now, product of the diagonal elements, also eigenvalues of L again will be diagonal elements. Inverse L inverse will be again. So, inverse of a lower triangular matrix is also a lower triangular matrix. Now, suppose I have two lower triangular matrix L1 and L2, both are lower triangular matrix, then L1 L2 is also a lower triangular matrix. So, the product of the two lower triangular matrix is also a triangular matrix, inverse of a lower triangular matrix is also a lower triangular matrix. The determinant is a product of the diagonal elements and the eigenvalue is also the diagonal elements. So, that is the some properties of the lower triangular matrix. Similarly, if I take the U as a upper triangular matrix, U11, U12 up to U1n, then U22 up to U2n, and in the last UNN, and all other values are 0. So, this is the upper triangular matrix. So, in this case also, if I take U, determinant of U, that is equal to product of diagonal elements, eigenvalues of U are again same as, so eigenvalues will be U11, U22, u n n. So, this will be the eigenvalues. Also same way u inverse is also an upper triangular matrix. Okay. If I take product of u1 u2, then it is also upper triangular. So, from here you can see that it is very easy to work with lower triangular or the upper triangular matrix. Even if you take the, because we have also discussed the D, the case third case the diagonal matrix. So, from here you can see that the diagonal matrix is like this one, A11, A22, ANN, and all the terms are 0. So, it can be treated as a lower triangular matrix or the upper triangular matrix. So, from here we can see that the determinant of D is again A11, A22, ANN. Eigenvalues are same as A11, A22, ANN. So, the same way, and the inverse of the diagonal elements, inverse of diagonal matrix will be 1 over A11, 1 over A22, 1 over ANN. So, that will be the inverse of the diagonal matrix. So, that is again the diagonal matrix, and D1, D2 is again the diagonal matrix. So, D1 and D2 I am taking two diagonal matrix, I am multiplying that one. So, that is also the another property of the diagonal matrix. So, we can from here we can see that the lower triangular, upper triangular diagonal matrix are very easy to work with. So, our next purpose is to transform my any matrix A into either of this form. Now, we few more properties of the matrices we want to define. So, let us define some important matrices. The first one is, we call it tri-diagonal matrix. So, tri-diagonal matrix is a matrix in which we have non-zero element at the main diagonal, super diagonal and the sub-diagonal, and all other values are 0. So, this is called the tri-diagonal matrix. So, tri-diagonal matrix we can define as A I j are 0, j is less than I minus 1 and j is greater than I plus 1. So, all the values I j 0 when j is less than I minus 1. So, below this, and j is this one is more than I plus 1. So, this is the tri-diagonal matrix. Similarly, I can define pentadiagonal. So, in the pentadiagonal matrix the same way, we have main diagonal, sub-diagonals, super diagonals, and all other values are 0. So, in this case this will be the pentadiagonal matrix. The second one is, so this matrix is also called the band matrix, because we have 3 bands here, we have 5 bands here. Okay, so, that is the banded matrix. Now, we define the sparse matrix. So, a matrix A, so that is n cross n I am writing, is a sparse matrix if if its almost all elements are 0. So, which contains only very small number of elements which are non-zero, otherwise all the elements are 0. So, that is called the sparse matrix. So, basically this is a band matrix, so you can also call it as a sparse matrix. It is a, suppose I have a 10 by 10 matrix and this is tridiagonal. So, that it can also be called as a sparse matrix. So, the matrix is called a sparse matrix if almost all the elements are 0 except the few ones. So, this is the definition. So, we will stop today here. So, today we have started with some matrices, lower triangular, upper triangular, and some properties of that one. So, in the next lecture we continue with this one. So, thanks for viewing, thanks very much.